Our journey begins at the source, where specifically engineered potato varieties are harvested. For industrial precision, mechanical harvesters extract up to 50 tons per hour, minimizing damage to the tubers. The raw crop is immediately transported to dehydration units to be processed into stable flakes. At the molding facility, potatoes arrive already transformed into high-purity dehydrated flakes. A closed-loop pneumatic system prevents external contamination during intake. Traveling at high velocity, the flakes are moved to centralized storage silos. Silos hold enough material for 24 hours of continuous production, ensuring zero downtime. Precise weighing is critical. Each batch must match the recipe with 99.9% accuracy. Moisture and purity are tested for every batch to ensure the perfect crunch. Advanced vibratory screens sort the material by density, ensuring a uniform dough consistency. From the silos, the material is diverted to specific mixing lines. Based on production demand, the first phase is complete. The raw material is ready for the transformation into dough. Before mixing, the dry base undergoes a final multi-stage purification process. Rare earth magnets capture any microscopic ferrous particles, ensuring absolute safety. Automated clean, in-place systems sanitize the entire line. Between batches, pure ionized water is prepared, ensuring the dough maintains a perfect molecular bond. Cornstarch and rice flour are added as stabilizers, giving the chips their signature structural snap. Advanced optical sensors scan 50,000 particles per second, identifying even the smallest discoloration. Precision air jets eject impurities without interrupting the flow of pure ingredients. Before hydration, the dry mix is brought to a specific temperature to ensure uniform water absorption. A 2-minute dry mix cycle homogenizes the starch distribution throughout the batch. Metering pumps calibrate the exact volume of water and emulsifiers required for the slurry system. Pressure is stabilized to ensure the high-speed injection occurs without cavitation. The preparation phase is complete. The material now enters the heart of the molding process. In the high-speed mixer, the dry base is met with a high-pressure infusion of liquid components. Liquid is injected in an atomized state to prevent clumping and ensure immediate absorption. The transition from dry powder to uniform dough occurs in less than 10 seconds. Automated viscosity sensors monitor the dough's resistance, adjusting liquid levels in milliseconds. pH levels are balanced to maintain the natural color of the potato and prevent browning. Continuous feedback loops ensure the dough's humidity remains within a 0.5% tolerance. The dough achieves its final consistency, a perfectly smooth mass, ready for the high-pressure rollers. Gravity-fed discharge moves up to 2 tons of dough per hour onto the primary transport line. Fragmentation ensures the sheeting rollers receive a constant, evenly distributed supply of material. Vibratory distributors level the material to within millimeters, preparing for the first stage of compression. Dough meets the primary rollers, where thousands of pounds of pressure begin the transformation into a continuous sheet. In the gap, individual dough pieces are cold pressed into a monolithic grain-free sheet. The dough has now become a sheet, the primary substrate for the molding process. Secondary calibrating rollers reduce the thickness to a precise 8/10 of a millimeter. Non-contact laser micrometers verify the sheet's profile in real time, across its entire width. Hydraulic servos apply 5,000 pounds of force, holding the rollers to within a micron of their setting. Filtered air stabilizes the sheet surface temperature, preventing sticking in the final molding stage. The final lamination stage ensures the sheet is perfectly flat and within a tolerance of 5 microns. Visual inspection systems monitor the web for structural integrity before the cutting process begins. Docking rollers perforate the sheet with microscopic holes, ensuring the final chip remains flat and bubble-free. Side trimmers remove uneven edges, establishing the final width of the dough web. Zero waste engineering immediately recycles all trimmings back into the initial dough phase. Controlled tension prevents the ultra-thin web from sagging or tearing during transport. A microscopic layer of cornstarch is applied, acting as a natural lubricant for the high-speed cutter. The infinite sheet now travels at peak velocity toward the shaping heart of the facility. Dancer arms provide instant mechanical feedback, stabilizing the web against minor motor fluctuations. Preparation is complete. The sheet enters the secondary phase. High-precision geometric shaping. A precision-engineered rotary die stamps out exactly 4,000 oval shapes every minute. Precision blades maintain a sharpness tolerance of 5 microns to ensure clean edges without micro tears. The dough lace is gently lifted away, leaving the discrete chip preforms perfectly aligned. High-velocity pneumatic intake ensures all excess dough is recovered without manual intervention. Thousands of individual dough preforms are now perfectly aligned for the curved molding stage. Automated loaders transfer the ovals into their individual curved saddles with millisecond timing. Optical centering sensors verify alignment before the hydraulic molding sequence begins. Hydraulic pressure gently forms the parabolic curves, a shape designed for both strength and perfect stacking. Mechanical clamps lock the molds in place, maintaining the chip's geometry. Throughout the frying cycle, up to 10,000 chips are aligned in parallel rows, ensuring maximum throughput in the frying tunnel. Precision fit within the saddle prevents edge curling, a critical factor for the final stackability. The line now enters the immersion tunnel, where the chips will meet oil, heated to exactly 180 degrees. Upon contact, the moisture within the dough instantly vaporizes, creating the microporous structure of the chip. Synchronization is absolute. Any deviation in speed would compromise the moisture removal cycle. While submerged, the chips are shielded from oxygen, preventing unwanted oxidation of the oils. The primary transformation is complete. We now enter the deep frying tunnel for precision moisture removal. In the deep frying tunnel, the chips travel through 3 distinct temperature zones for even cooking. In Zone 1, high heat rapidly ejects surface moisture, creating the chip's unique cellular structure. Steady transit ensures that every chip receives an identical thermal profile from end to end. Continuous thermal monitoring keeps the oil within a 0.5 degree variance. The oil is continuously filtered and polished, removing particles to maintain absolute clarity and flavor. In the final zone, the Maillard reaction completes, developing the classic golden hue and nutty aroma. Sophisticated software synchronizes frying time with line speed to within a fraction of a second as the chips emerge. They have reached their final structural geometry and a moisture content of less than 2%. Initial gravity drainage recovers up to 15% of surface oil for immediate filtration. Centrifugal force strips away microscopic oil layers, resulting in a cleaner, less greasy texture. High-capacity extractors remove leftover frying vapors, maintaining the factory's air quality and temperature. Once cooled slightly, the mechanical locks are released, preparing the chips for demolding. Ultrasonic transducers create micro vibrations, ensuring a perfect release without damaging the delicate chip edges. Laser profiling checks every single chip's curvature to ensure they will stack flawlessly in the final canister. Flash cooling locks in the structure and prepares the surface for the electrostatic seasoning stage. Acoustic sensors measure the crunch frequency, verifying that every batch meets the signature crispness standard. In the tertiary phase, the bare chips receive their characteristic flavoring. Through precision application systems, chips are fed in a continuous waterfall to ensure maximum surface exposure for flavoring. Electrostatic nozzles charge the powder particles, ensuring they cling evenly to every curve of the chip. A 72-inch tumbling drum gently folds the chips for 90 seconds to achieve flavor homogeneity. Infrared spectrometers analyze the coating thickness, maintaining flavor consistency across millions of chips. Declamation systems recover 98% of airborne seasoning, recycling it through sterile filtration loops. High-intensity lighting allows for a secondary visual check, ensuring the color profile matches the brand's global standards. Automated air knives eject any chips that fail to maintain their geometric integrity during the seasoning tumble. Geometric dividers organize the flow into multiple parallel lanes, preparing for high speed. Automated counting optical sensors count every unit, ensuring each canister will contain the exact weight promised on the label. Line speed is synchronized with millisecond precision to prevent chip overlapping during high-speed transport. A final pass through a triple coil metal detector ensures the product is free of any metallic contaminants before sealing. Three-dimensional laser profiling measures the volume and weight of the seasoned chip to a fraction of a milligram. Polished V guides gently funnel the individual chips, aligning their centers with a tolerance of less than 1 millimeter. Micro vibrations eliminate surface friction, allowing the chips to find their exact natural center within the transport rows. Processing is complete. We now enter the stacking phase, where raw engineering meets high speed. Consumer packaging, ACT8 stacking and finalization. The chips are now funneled into vertical chutes to begin the nesting process. Gravity and geometry work together. The parabolic curve of the chips ensures they nest with zero air gaps between them. Electronic fingers catch and release each chip at 200 units per minute, building the perfect column. Laser height sensors verify the stack count to ensure it fits perfectly inside the 158mm canister. In the buffer zone, stacks are staged in parallel, allowing for synchronized feeding into the high-speed canning modules. A gentle top-down compression verifies the nesting density, ensuring no bridge gaps exist within the column. Laser profiling detects shingled or misaligned chips that could compromise the airtight seal of the final canister. Finals micro vibrations allow gravity to finish the nesting, creating a monolithic column of product. Stacks are shuttled at speeds of 3 meters per second into the final assembly modules. Anti-static grounding prevents chips from sticking to the canister walls during insertion. Each batch is weighed to within 0.1 grams, ensuring consumers receive the full stated amount. Final chrome extraction ensures that only whole chips and their flavoring enter the canister, maintaining aesthetic purity. The timing gate synchronizes the arrival of each chip batch with its corresponding canister at the assembly mouth. A final visual confirmation by artificial intelligence verifies stack integrity one last time. The finalization phase is complete. We now enter Act 9, the high precision assembly. Into the final protective environment, precision canisters arrive from a sterilized feed line, ready for high-speed integration. High pressure. Ionized air removes any microscopic particles, ensuring the canister is perfectly sterile. Before insertion, the handshake moment. Chip columns and canisters are aligned with micrometer precision for seamless insertion. High-speed plungers insert the batches in less than half a second, nesting the product into its protective shell. The insertion stroke is calibrated to the exact depth of the canister, leaving precisely 10 millimeters of headspace. Modified atmosphere. Packaging replaces oxygen with nitrogen, extending shelf life and preserving the chip's fresh aroma. Induction sealers fuse an aluminum membrane to the rim, creating a hermetic barrier against moisture. Thermal imaging confirms the heat distribution across the seal, guaranteeing zero leaks. Secondary capping provides mechanical protection and resealable functionality for the consumer. Canisters are oriented to expose their base for laser, lot coding, and expiration dating. Assembly is complete. The product now enters the final phase. Rigorous quality control and finishing. Act 10, quality control. Every single unit is weighed to ensure compliance with global labeling laws. With an accuracy of 0.1 grams, the load cells detect any overfill or underfill in milliseconds. Advanced X-ray scanners peer through the metallic canister to verify stack orientation and identify any foreign particles. Machine vision cameras inspect 360 degrees of the canister, ensuring every label is perfectly applied and defect-free. Fiber lasers engrave permanent traceability data directly into the metal base, creating a tamper-proof record of the production run. Automated squeeze tests monitor internal pressure, identifying even the smallest pinhole leaks in the hermetic seal. Random manual sampling provides a final sensory check on flavor, texture, and aroma. In the on-site lab, fully inspected, units are diverted into dedicated packaging lanes, ready for the final logistical stage. A final external polish ensures the packaging is pristine before entering the multi-pack assembly line. With all parameters verified, the batch is officially released for global distribution. The individual processing acts are finished. We now begin the final logistical grouping. ACT11 packaging and logistics. Automated grouping modules organize canisters into consumer-ready trays. High-speed pushers group 12 units every 3 seconds, maintaining perfect label alignment. Heat shrink film stabilizes the group, creating a single secure logistical unit. Robotic case packers handle up to 6 master cartons per minute, ensuring a constant flow to the warehouse. Every master case is labeled with unique tracking data, enabling full traceability. From the factory to the retail shelf, robotic palletizers build 8-foot-tall columns of product, optimized for container space efficiency. Pre-stretched film applies over 2,000 pounds of containment force, locking the entire pallet into a single rigid block. Act 12 distribution. Autonomous vehicles transport the finished loads to fully automated, high-bay storage, climate-controlled storage. Preserves the product's quality until the precise moment of shipment. From here, these batches will travel thousands of miles to reach consumers in over 80 countries. Pure engineering, perfect geometry, and absolute quality. Engineering the future of food. 100% precision. 100% quality,